So in this problem, we have light incident on a bubble. We see that orange light is strongly reflected, and we're asking how thick is the bubble. So let's see what we can figure out. Let's draw a small sketch of a part of our bubble surface. So let's say that the bubble looks like this. There's air on the outside, so N1 equals 1. There's soap, that's what the bubble is made out of. That's N2 equals 1.33. Then inside the bubble again, there's more air, so N3 equals 1. Let's think about the light and what that means in terms of our interference. So light is incident on the soap bubble. Part of that light goes through and part of that reflects. So at the air-soap interface, at this interface right here, N1 is less than N2, we get a pi phase change. So this reflected wave has phase shifted by pi radians. So then the light also hits the soap air interface, and then part of that light goes through and part of that light reflects. What happens at this interface? At this one, we see that N2 is bigger than N3. Okay, so this index is bigger than this one. This goes from a heavy to a light, so that's a 0 phase change. So this one is 0. So if we look at these two reflected waves, these two waves are out of phase. So that tells us that our delta phi naught is equal to pi. Okay, so now we've established the relationship between these two reflected waves. So now let's ask, what else are we trying to sort out? We know that orange light is reflected. The wavelength of orange light in a vacuum is 600 nanometers. It's strongly reflected, so we're talking about constructive interference. So let's write down our condition for interference. So constructive interference says that delta phi is equal to 2 times pi times delta x divided by lambda. This is the lambda in the material. It's the lambda in this material right here, so it's lambda in N2 in the soap, plus delta phi naught. And our condition for constructive interference is that it's a multiple of 2 pi, an even multiple of 2 pi. M equals 0, 1, 2, and so on. So let's see what we're going to fill in here. What is delta x? Well, let's think about delta x. Delta x is how much farther does this wave travel compared to this wave. So this wave has to come in and bounce back and come right back out. So if this has a thickness of t, then delta x is equal to 2 times t. Because this light ray has to go through the soap bubble once, it has to bounce off and come back. So this one doesn't travel in the soap bubble at all. This one goes through twice, so the total delta x is 2 times t. Lambda N2 means what's the wavelength of the light inside the soap bubble. We know that lambda N2 is equal to the lambda in the vacuum divided by N times N2. And delta phi naught is our phase constant, so that's pi, so we can put that in. Let's put those together and see what we have. So we get delta phi equals 2 times pi times 2 times the thickness divided by lambda. N is in the denominator of the denominator, so that puts it up in the numerator, plus pi equals m times 2 pi. What we're trying to find is the thickness, so we're doing okay. We know N2, we know lambda, we don't know m. Let's see if we can figure out m. So why don't we go ahead and solve this equation for t. After we've solved for t, let's decide what do we need to have for our m value. So 2 times 2 is 4, so 4 times pi times the thickness times N2 over lambda equals m times 2 pi minus pi. And then we want to cross multiply our lambda up here. T is equal to m times 2 pi minus pi times lambda divided by 4 pi. Okay, there's our expression, divide by our N2 as well, so we don't forget the N2. See that we've got, why don't we take our pi outside up here? So that's m times 2 minus 1 times pi times lambda divided by 4 pi times N2. See that those pi's cancel, so our thickness is equal to 2 times m minus 1 times lambda divided by 4 times the index of refraction. So let's remember, m is allowed to be any integer. M equals 0, 1, 2, 3, and so on. So we'll ask which m is the correct m if we want to have a thin bubble. So those are the m's we're allowed to have. And we're going to assume we want a thin bubble. So now let's see, what does that mean? So if we put in our first value of m, if we put in 0, we'll get minus 1 times lambda over 4n2. Well, that doesn't make sense. Our thickness is not going to be negative. So let's not put in 0. Let's try 1. So t is equal to 2 times 1 minus 1 times lambda divided by 4 times n2. This one looks pretty good. 2 times 1 is 2. Take away 1 gives us 1. That's lambda over 4 times n2. We can put in the numbers that we know. Lambda is our wavelength of orange light. That's 600 nanometers. Divide that by 4 times the index of refraction, 1.33. Put that through the calculator and we get 113 nanometers. That's a pretty thin little soap film, and we can figure out that thickness just by thinking about the color of the reflected light, so that's kind of neat.